Greetings, my name is Gabriel Aviles Cordero, and I will be presenting Phase C1 of the Capstone, which will be focused on the mechanical subsystem of a continuous passive motion device, otherwise known as a CPM. In this phase, we will be focusing on the following points. 1. The interface diagram. 2. The detailed analysis or design studies. 3. Design specification and drawings. 4. Verification. And 5. The project plan. As previously mentioned, let's start with the interface diagram proposed in Phase B. In it, we specify the following. The CPM device is a medical product intended to provide physical rehabilitation assistance to various patient groups. Our system should be able to support joints of the lower extremity of the body, with a major emphasis on the knee and ankle. By this means, the product should be able to accommodate patients with a maximum length of 150 centimeters and in the ankle 80 degrees. We assume optimal humidity and temperature. This is for the purpose of finding, in the knee system, the pulley diameter 2, the belt length, contact angle, pulley spacing, belt speed, and in the ankle system, the input and output gear ratio, and finally, the number of teeth. In our interface requirement diagrams, we also made some additional assumptions. In our knee system, because we're using a pulley system, our assumptions are our motor is a stepper motor. Our inlet torque is 60 newtons meters. Our inlet angular velocity is 1000 RPMs. Our motor potency is equivalent to 6,283.1853 watts. Our pulley diameter 1, or the driver pulley, is about 3 centimeters or 1.18 inches. In our outlet angular velocity is 400 RPMs. Our outlet torque is 150 newtons per meter in the max torque. The center distance between pulleys is 8 centimeters. In our ankle system, we also use a stepper motor with our inlet torque of 20 Newton meter, our power inlet of 100 watts. Our type of gear is a bevel gear, and the number of teeth in our gear 1 is 18. In our detailed analysis or design study, we want to find our unknowns. The first unknown is the diameter of the pulley 2. So to find the diameter of the pulley 2, we use the equation diameter of pulley 2 divided by diameter of pulley 1 equal the angular velocity of the inlet and divided by the angular velocity of the outlet is equal to torque outlet divided by torque inlet. If we clear our equation to diameter of pulley 2 or D2, we obtain a diameter of 2.9528 inches or 7.5 centimeters. After obtaining the diameter of pulley 2, we then try to obtain the contact angle of pulley 1, and it's identified as zeta D1, in which we say pi minus 2 arc sin multiplied by D2 minus D1 divided by 2 multiplied by C, which is the central distance. We obtain a contact angle of the pulley 1 of negative 29.523 degrees. For the contact angle of pulley 2, we obtain an angle of 35.812 degrees. After obtaining both contact angles of both pulleys, we then switch to search for the valve length, in which valve length is defined as 4 multiplied by C, or a center distance elevated by 2. The result of that multiplication, we then subtract d2 minus d1 elevated to the 2 elevated to 1 divided to 2 plus 0.5 multiplied by d2 by contact angle of pulley 2 plus d1 by contact angle of pulley 1. That gives us a valve length of about 6.6634 inches. Finally, we also obtain a valve velocity in which we define it as pi multiplied by d1 multiplied by angular velocity of inlet divided by 12. As a result, we obtain a valve velocity of 32.3805 inches per second, or 0.8225 meters per second. These measurements were obtained using the table of flat belts and flat pulleys. Of which only 40 inches will be used. The diameter of the lead screw is about 1.27 centimeters, and it should be equal to 0.5 inches, give it or less. The screw pitch, it would be 0.5 minus 10 for one pitch. That means that the lead will be 0.100. These definitions give us the distance between teeth, which means that it will have 10 teeth per inches. If we use this information, we convert the linear movement or displacement into revolutions per minute, or RPM, in the bar or threading. The outcome of the angular velocity, or RPM, is the linear displacement divided by the lead pitch, which is 39.9405 inches per minute divided by 0.1 inches per revolution. That gives us an angular velocity, or a lead screw velocity, of 399.1 405 RPMs, or basically 400 RPMs. Continuing to our ankle system in our detailed analysis or design study, our design is a straight bevel gear which are usually used for pitch line velocity up to 100 feet per minute or 5 meters per second, with a noise level that is not important in the consideration. They are available in many stock sizes and are less expensive to produce than other bevel gears, especially in small quantities. The design used provides us with a bevel gear 1 which when a quantity of 18 teeth and a modified bevel gear 2 structure. As mentioned above, the range of motion of the ankle of our interested project is about 80 degrees maximum. In the bevel gear 2 does not meet with the correct measurement of displacement of 80 degrees, it exceeds the 120 degrees. Therefore, it is necessary to find the correct gear ratio between the two gears and to be able to define the correct, which is the right design to obtain the correct range. According to the given design, bevel gear 1 has a diameter of 1.5 inches with a number of teeth of 18, which means that bevel 1 or BG1 is equal to 1.5 inches, and also means that 1.5 inches equal to 3.8 centimeters. And as mentioned before, a number of teeth of 18. On the other hand, the bevel gear 2 is not a complete gear but a modification that only shows part of or 90 degrees of a side or of a circle. Within this gear, the author defined 18 teeth also. Therefore, we can define the gear ratio as BG2 T, which means the number of teeth in the gear 2 equals 18 multiplied by 4, the 4 planes of the circle. That gives us a BG2T, or the number of T in the gear 2 of 72, which means our gear ratio is about 4 to 1. Having this information, then we can define or say that the diameter of the gear 2 is about 15.242 centimeters or 6 inches. Continuing with our ankle system, we chose a 20 Newton per meter stepper motor that will use a power of 100 watts or 0.1341 horsepower. Our power input, or it was P1. P1 is 100 watts, and also we have a torque or input torque of 20 Newton per minute. By obtaining the gear ratio, the torque, and defining our power 1, we can calculate the following. The torque output, or torque 2, of our gear will be 80 newtons per meter. Now we're going to talk about our design specifications and drawing of our systems, starting with a knee system. In our knee system, we're going to start with our pulley belt drawing, which you can see right here. Next, we can see the drawing of the pulley 2, which is the bigger one, or the drive one. Here we can see the drawing of pulley 1 and its dimensions. Next, let's see our design specifications and drawing for our ankle system, and starting with our gear bevel 2. following by our gear V1, and lastly followed by our footrest platform and motor housing, and our Arduino and driver housing. After defining and showing our drawings for both ankle and knee system, we now jump to our verification step. In it, we verify our MOPs for mechanical subsystems, our performance, the phase in which it was defined, and if it complies or not. Our MOP selectors are the torque output needs, which is about 130 newtons per meter. The torque output of the ankle, which is 40 newton per minute. The range of movement, which is we have two for the knees and 2 for the ankle. And that was defined in phase A. The 2 previous ones were defined in phase B. The motor power in the knee is of 150 watts, defined in phase B. The motor velocity in the knee is about 1000 RPM, defined in phase B and phase A. The bevel gear have a number of 18 teeth, mentioned in phase B. The operational weight is about 8 pounds for both, in combination for both systems, and that was mentioned or indicated in phase A. The operational temperature that must be between 30 to 40 degrees Celsius was defined in phase A. The investment cost, in which we specified that ideally each model should cost no more of $400. We have the model used in the knee system of $420, which is basically in range of that was previously stipulated, and an ankle model cost of $193, which is below below our max, which means we comply. And finally, our range of movement should be of 150 degrees in the knees and 80 degrees in the ankle. Thankfully, all our MOPs complies and our performance complies with the previously mentioned in phase A and phase B. Finally, now we present our project planning, in which we prepare for phase 2C or C2. Thank you for your attention, and I hope this presentation is useful for you.